So, hi everyone. I'm Chahat, a PhD student at NCRA. In the previous talks, you heard about technical side of Spotlight, how it works from correlator to candidate optimization and localization or imaging. In my talk, I'll focus on how we use these capabilities for FRB science, basically how we study emission physics. So here I start with the quick reminder of what FRBs are. So FRBs are extremely short, bright radio pulses which last only for a few milliseconds. So FRBs doesn't always show a simple single clean pulse, but sometimes they show interesting features, as shown here in the example taken from Hessels et al. Some of them show microstructures and multi-component subburst and band-limited emissions. So these fine time frequency structure helps us to reveal about the emission physics and what's happening near the source. Next interesting property is polarization, which has been already covered by Surya on day 2. And so I'll not go in the more detail of the polarization. And so for the to study FRBs in great detail, we need high time resolution. Suppose we observe an FRB at coarse time resolution. So we'll just detect a single pulse, but we'll not able to see if there are any structures present within the single burst. So if we observe the FRB at microsecond resolution, so we may get several substructure within it. So for say for an example, in the left plot, this is plotted at time resolution 16 microseconds. So look at this gray panel, gray region where it is looking like a single pulse, kind of single pulse. But when we move to 1 microsecond time resolution, then we may see several subbursts here present. Like this time resolution is of the order of milliseconds, but this gray region here, and when we plotted here, it is showing of the order of microsecond duration. So from microstructure study, we can say that our progenitor is very compact. And now to study FRBs in more detail, what we need flexible time resolution, which varies from microsecond to millisecond, and we need an instrument which is capable of polarization, and we as FRBs last only for a few milliseconds, so we need a follow-up in real time. So Spotlight exactly delivers all these science needs. So for flexible time resolution, it gives us Nyquist sample baseband data, and for polarization, it also gives high time resolution polarization data from baseband data. And for real-time follow-up, it also gives us VO events, and it also, in the real time, it also gives us the burst classification and imaging. So in the previous talks, you have seen this plot, like how this, you have seen this plot. So when a detection happens, so it triggers the data dump. It dumps beamform, baseband, and visibility data, and then it goes to discovery database. So after discovery database, it automatically estimates parameters, and if required, it sends triggers through VO events and ATIS, and all these happens in real time, like from the signal coming at GMRT and the trigger through VO event. So everything is happening in real time, but this baseband processing, the high time resolution study happens in offline. So this is how the discovery database page looks like. On this page, you can see a transient detection summary in real time and the past events also. So when you click any of this real time or history page, it will show this kind of page, all the epochs. And next, it will show this kind of page where it will show detection in classified page along with many characteristics like its probabilities, MJD, RAD, frequency, SNR, DM, and all that. So when we click any of this detection in classifier, so we get this plot and this plot. So this is for the pulsar J1731, which was detected in L band. And this is another example. This is for pulsar BO740. So, which was detected in band 3. So, from this, we can say that our pipeline is working well across different bands. And once a burst is confirmed, it automatically estimates parameters using a module that is BURFI, which stands for burst fitting. And it automatically calculates these parameters, that is pulse duration, scattering time scale, emission bandwidth, peak frequency, and fluence. And after this, it triggers events through this VO events. And now we have developed a software for VO events. We have developed a software for VO events which can send events to different observatories. We have tested this software with LIGO India. So we have received trigger messages from LIGO India. So Spotlight isn't just observing the sky, but it is making multi-messenger astronomy possible. So the takeaway of this slide is, as we detect the data, it directly goes to database, estimates these parameters, and sends alerts to different observatories for follow-ups. Now moving to the offline processing. After real time, we generate coherently de-dispersed full stocks beam from Nyquist sample baseband data. And for spectro-tempo-polarimetric analysis, we first do fine DM search. After that, we just fit in the frequency and time domain. And for polarization study, we first generate stocks IQ UV parameters. And for calibration of polarization, we use noise side scan, as Surya also mentioned in his talk. So from this input, we extract these parameters, such as like from spectro-tempo thing, we get microstructures and drift rate. From polarization study, we get the idea of linear and circular polarization friction. We get an idea of RM value and how PA is varying, whether it is flat or varying. So from offline processing, we get main idea of spectro-tempo-polarimetric study. Next is the case study. This is the example of FRB 1809160. So this is from beam forming data, and this is a single clean pulse. This is showing a dynamic spectra. It is showing a band limited emission, and this is the intensity time plot. This is frequency, intensity frequency plot. We have fitted this using exponentially convolved Gaussian, and this has been fitted using just a Gaussian. So we extracted parameters from here, like from time intensity plot, we extracted intrinsic width and scattering time scale. And from this intensity frequency plot, we get peak frequency and emission bandwidth. And for this is for the polarization, this is the same data. So this is just the Stokes I, and this is showing Stokes I and another Stokes parameter, that is L and V. L is linear polarization, and this is circular, and this top panel is showing the PA. And these are the real bursts on which we have applied BURFI. So BURFI is working well with single pulses and few of the multi-components, but we are working on automation of multi-components. So this work is ongoing, automation of multi-components and profile fitting and polarization. Next is, so we have analyzed data, we have fitted this. Now the question arises, what science we can expect from all this FRB study. So first aspect is we see burst properties. From burst properties, we see its spectro-tempo analysis. From spectro-tempo, we just generate dynamic spectra and profile. It's just a frequency integrated time profile. It gives us sub-bursts, like as shown here, and it also gives us drift rate. Also, it gives us the energy distribution like this. So, and polarization also, like it also comes in the burst properties. I'll discuss more science about these plots in my next talk. It is on 14th October. And next aspect is repetition in activity. So from this we can generate a waiting time distribution plot. Waiting time is nothing but just the difference between time of arrival of two consecutive bursts. So we also generate this type of plot, and from nearby bursts we also see if there is any periodicity or quasi-periodicity present or not. And from multi-band observation, we also see if there is any frequency-dependent activity happens or not. Again, we'll discuss these plots on 14th October. And next aspect is propagation effects. So from propagation study, we measure this scattering, scintillation, DM and RM. So Viswesh will talk on scattering and scintillation in the next talk. And so if we combine all these properties like burst properties, waiting time and etc., propagation effects, so if we combine all these properties, through these properties we can see what's happening near the source. It can reveal the progenitor physics about emission mechanism and local environment near the source. So this is the summary, and I think I have completed in 10 minutes, I guess. The content was...
All right, time for plenty of questions. Oh.
Hi, very nice talk, thank you. You mentioned you are estimating the drift rates as well. Can you say how you do that?
So currently I'm using Clunis code, the DFDT. So it takes a region around the dynamic spectra and a noise around the dynamic spectra. It then takes generates a 2D autocorrelation. On top of that, it makes a 2D Gaussian, and the slope gives us the drift rate. That the formula is tan theta is something like that. df by dt gives us that. So it is something related to slope. When we take a 2D Gaussian and it gives us a slope, it gives us the drift rate value. Yeah.
Any more questions?
Hi. So how can we relate to the magnetic field structure? You said the polarization measurement.
So here, if there is a swing in PA, it suggests that the magnetic field is not in random in nature, but it is structured or twisted. And here you can also see that we are also getting circular polarization, the left-handedness and right-handedness. So from PA, we get an idea of RM, and from RM, we get the idea of magnetic field. So
okay.
Right, I guess I have a quick question actually. So you mentioned that you're going to do polarization calibration using noise diode observations.
yes.
So I guess these are your detections that are coming from commensal searches, right? So is it guaranteed that there's always going to be a noise diode observation for a particular observation? Because someone might not need polarization data, right, for their science.
Yes.
And so then how are you going to guarantee that you have the calibration solutions to get, you know?
Jayanta, can you explain that from that observing schedule, if we have detections, like if we have some black slot available, so...
No, I think this is a constant. Any kind of commensal observation is difficult because it's not, the observing setup is not decided by us. So we do two kind of, I think when Surya's talk was that there's two ways to calibrate it. One is that you observe a noise diode or you observe a polarized source. And observe polarized source is even more difficult because somebody will go to sacrifice their time to observe another source which may be different direction of the sky. So then that's why we thought maybe noise DAO is useful. And again, noise DAOs, nobody will sacrifice their observing time. So the way you will do it, again, observatory will have their own time. So basically you have a something called a gray slots in observatory, which basically where, anyway, this has to be kind of first formalized inside that. But from the development point of view, you actually developing a pipeline where you have a nearest time of observation. Like when you detect FRB at a given time, nearby to the time, we have a gray slot available in the system where there is a noise DAO baseband data will be recorded. And that noise DAO baseband data will be used to calibrate your data, which could be a few hours apart. Okay. So it's uncertain territory where it will be going. But currently that's the conventional observation, that's the best. So you can only take observatory time to have a scheduled noise DAO switching happening at a regular interval.
Thanks. Any other questions for Chahat? If not, let's thank Chahat again.